Doctor, I can't share my screen. We are all using the same account because we are sharing one laptop.
Okay, well, no problem. Understood. Okay. Can start.
Uh,
Or share slide.
I can't share my screen. It said that host disabled participant screen sharing.
Try again.
Okay.
Okay.
Yeah. Mm. No, because can't see full screen. Okay. Okay, Doctor, so can we start now?
Start.
Okay. Good afternoon, Prof. So we are Group 8 and we are from Section 5, and this is our group assignment presentation. So these are members. I'm Wong Jo Yin.
Prof, I'm Yo Yun. Hi, Prof.
Hi.
I'm Imeng Fong.
Hi.
Assalamualaikum, Doctor. I'm Muhammad Faizi.
Salam. Okay, proceed.
Okay. So our assignment question is B3. So this is the given system. It is a Sunseeker system. And this is the given block diagram and our system parameters. So the Sunseeker system, it aims to control the altitude of a space vehicle so that it will track the sun with high accuracy. So we are going to analyze the system in time domain and frequency domain and figure out the most optimal controller or compensator to optimize the system response. So our objective of this assignment is to compare the results between manual calculation and simulation of the system, to analyze the suitable methods to optimize the system response, to improve the system performance, and to compare the difference between the system compensation using different methods. So task 1 is mathematical modeling. So using the given block diagram, we can obtain this general equation for the open loop transfer function by using the block diagram reduction technique. So this is the obtained open loop transfer function, and this is the obtained closed loop transfer function because there is a unity feedback. Then through MATLAB simulation, we can assign the values to each of the variables, and we can write the same equation in the MATLAB script. So through the command window output, we can see that the obtained open loop and closed loop transfer function is the same as the calculated functions.
Stop. Question. Coding.
Yeah.
Coding T equal to feedback bracket G multiply K comma 1.
Yeah.
1 stands for what?
The unity feedback.
Unity feedback. Okay.
So this is task 2, which is the system analysis in time and frequency domain. So based on the manual calculation, we can obtain the characteristic equation from the closed loop transfer function, and then we can create the RH table. So based on the concept of the RH table, the first column must all be positive for a stable system. So the third row, which is the K, must be larger than 0 because K must be a positive value. So there is no upper limit of the K. That means the K critical is infinity. And this means that no matter how much we increase the gain, the system will always be stable. So when we sketch the root locus, we can also double confirm this because, okay, we can sketch the root locus by using the open loop poles. And as we can see, based on the root locus sketch, we can obtain the breakaway point that we calculated, which is negative 12.014. And the imaginary crossing, there's no imaginary crossing because the open loop pole is right at the origin.
Stop.
Yeah.
Can you forward, please? Okay.
Okay.
What is the breakaway point?
The breakaway point.
The value.
The value -12.
Okay. What is the closed loop pulse at the breakaway point?
The closed loop pole at the breakaway point. -12.
Same. The closed
Closed
loop
loop.
pulse value at breakaway point.
The closed loop. Yeah.
Yes or no?
Yes.
Yes. Yes, what? Same.
Yeah.
Closed loop pulse and breakaway
The pole.
point is equal to -12.
Yeah.
Okay, correct. Proceed.
Okay. So from the generated root locus. Okay, so for the m-script file right here, I use the same equation, but above this equation, actually, we already assigned the variable values. So I just use the same equation, and using the rlocus function, we can generate the root locus graph. And based on the root locus, we can see once again, that the stability range of for gain k is k larger than 0, and the breakaway point is s equals to -12, and there is no imaginary crossing point. So this is the time response. Using the closed loop transfer function, we can generate the time response by using the step function for a unit step input. So these are the obtained peak time, settling time, percentage overshoot, and steady state error. So using the simulation, we can create the block diagram. And from the graph of the simulating, we can see that it is a similar graph to the one generated in MATLAB. And we can also obtain,
What do you mean by out.t with the clock in the
that is
simulation?
to do this step info function. Yeah, that is for the to workspace block.
And the clock on the left?
It represents the time for the x-axis.
Okay, all right.
So for more accurate results, we use the to workspace block. And then using this to workspace block, we can actually use the step info function in the command window, and we can generate all the response that we need. So we can obtain the peak time, the settling time, and the percentage overshoot. So by comparing the MATLAB and Simulink results, we can see that the results are pretty similar, but there are only slight differences because of the different algorithm that MATLAB and Simulink uses. So these differences may be due to the different numerical precision and integration methods used by the applications. So by analyzing so now we're going to analyze the system in frequency domain. And in frequency domain, these two lines are just extra, just for me to double confirm the gain margin and phase margin. So from the generated old plot, we can see that the phase margin is 17.3 degrees, and it occurs at the frequency 77 radian per second. So the gain margin is infinity, and this is because the system is stable at all values of k. So this means, as I said, like no matter how much k increases, the gain margin will still be positive. So the system is always stable.
Stop.
Yeah.
What is the value of the gain crossover frequency?
The gain crossover frequency, it's at infinity because the phase plot, it never reaches -180.
Oh, it's a 17.3 radian per second there when the gain
Huh?
curve cross 0 dB. Gain crossover frequency when the gain curve
Oh, that one is isn't that the
17.3
phase crossover frequency?
phase crossover frequency when the phase curve cross minus
Yeah.
180, which is unavailable lah, not available lah, because
Yeah.
it's infinity. All right.
Okay.
All right.
So since the system is type 1, we can obtain the steady state error by finding the KV constant. So from the boat plot, if we draw the line, the -20 dB per decade line, we can actually obtain that the KV is 200 radians per second. So the steady state error is around 0.005, and we can approximate it to 0, which is similar to what we expected from the other simulations. So using this analysis in frequency domain, we can also obtain the closed loop boat plot. And using this closed loop boat plot, we can obtain the peak gain. And using the peak gain, we can obtain the maximum magnitude by calculation. Then we can also obtain the peak frequency and the bandwidth. So the bandwidth occurs at the magnitude -3 dB. So using those values, we can obtain the damping ratio and the natural frequency. Then using both of these values, we can obtain the overshoot percentage, the peak time, and the settling time. So this is the comparison between the time domain analysis and frequency domain analysis. So the percentage error is all very low. It is less than 5%. So it can be said that our results are accurate because both of these analyses give us the same results. So yeah, our results are identical and the percentage errors are all very small. So that's it from me. If you have no other questions, I'll pass it to Yo Yu.
May I know, Wong,
Yeah,
where is your school last time? Your
my
school?
school last time.
Ah,
You mean
mana?
in secondary? Yeah.
Ah,
In Malacca, St. David High School.
Saint David. It's not a Chinese
Yeah.
school. It's the SMKA. SMK.
Yeah. Yeah.
Okay. No wonder lah dia cakap English dia. Okay.
Okay.
Some Chinese,
Because I
some Chinese
because
say,
I
some Chinese say
because I speak
zero
English at home.
zero. Some Chinese say zero zero. Their dialect is quite different lah. Okay.
Yeah. Okay, so now I'll pass it to Yo Yu.
Hi, doctor. So now I'm going to explain about task 3. So we are going, so since there is no steady state error, so we can just use PD controller, and then we we are planning to decrease our overshoot by 50%. So originally is 60%. We'll decrease to 30% to get a more stable system response. And this is our PD controller design. And we reduce the overshoot by 50%, so it's 30%. And also the new setting time is also reduced by 50%, so it's 0.163. So by the new setting time, we are able to get the view value. And from here, we can calculate the new dominant pole. And from the imaginary pole, we can get the new peak time, which is 0.049 seconds. And this is to calculate the theta z by using the triangular calculation. So we get the theta z is 31.44. And from here, we can get the uh, the z value, which is negative 167. And from here, we can calculate the K. The K is equal to 4.5 times 10 power of -3. And from here, we can calculate the KP and also KD. And then I put into the MATLAB code to test whether the K calculated is correct or not. So it's almost similar. And I put it into the Simulink. Yeah. And this is the
Stop. You have a blue line and dotted black line. So
ah
this legend, blue stands for what? Dotted stands for what?
the dotted one is before compensation, which is
Oh,
the original one, and then the blue one is after compensation, the new one with the KD and
okay.
yeah. And then this one is the Simulink, the step info, and then this one is the before compensation. The setting time is 0.29. and the new setting time is 0.14. So is obviously we decrease the setting time by 50% and also the overshoot by 50% because it's originally 61 and then now is 30. Yeah, that's all for me. Now I'm going to pass to my next teammate, the info.
Good morning, doctor. My name is Wing Fo. Good
Afternoon.
afternoon, doctor. Sorry.
You are back to the future.
Okay. So I will continue to my part is tuning of PID parameters. So the PID tuning is to adjust the parameters of PID controller to achieve the optimal performance of the system. So we're using the Simulink PID tuner for this part to use to achieve the best performance of the system. So we change the response time and the transient behavior, and this one is the step plot for the system. And the dotted line show the block response is before the PID tuning, and the solid line is after the tuning. So the table over here showing the control parameters and also the performance and robustness. Then for the gain margin or gain margin is infinity and the phase margin is 90 degree. Since both margin are positive, so the system is stable. By comparing the controller parameters and the performance before tuning and after the tuning, um, the proportional parameter are increased, and since the system have no steady state error, so we didn't use the integral parameter, and the derivative parameter also increased, and we also increase the filter coefficient. After the PID tuning, the rise time decreased and the settling time also decreased. The overshoot reduced to 0 and the stability remains stable. Because by increasing the KP, which make the system more responsive, so the system will reduce its rise time and also the peak time. The settling time decrease because the KD helps the system to minimizing the oscillation. So that's all for me. I will continue with part 5.
That's right.
Yeah. So,
Assalamualaikum and good evening, Doctor.
Hmm.
Next, I'm going to present task 5, which is to design a lead lag controller to improve our system. So we have the problem same as task 3, which is to reduce our overshoot and settling time to half. So the desired overshoot percentage is 30%, and the settling time that we want to achieve is 0.163 seconds. Then to design first we want to design a lead compensator only because we want to improve the stable and the speed of the response of the system, and we doesn't need lag compensator because we already have the steady state error is already 0. So to design a lag compensator, we need to find the desired uh, phase margin, which is 39.1 degree, and we need to find the GC of the lag compensator. So to find the GC of the compensator, we need to find the PC and ZC of the system. So first, by using the correction factor and minus the original phase margin, we get that it is 26.77 degree. and we will get the beta is 0.3789. And then we find the GC omega max, which is 1 over square root beta, and we will get it is at 1.6246 dB. And we need to find the not dB in K, and then we need to find the dB, which is 4.2149 dB. And we see the radian per second at that magnitude, and we will get it is 99 radian per second. Next, we move to finding the ZC of the system using the formula, and we will get that 60.9393, and PC is 160.8322. So the ZC should be smaller than PC for a lag compensator. So this is a like logic value, and we will get the GC of the overall for the lag compensator.
Stop.
And
Reverse.
wait,
Reverse.
okay.
What is the gain value for the lead compensator?
Gain value for the lag compensator,
Value of the lead compensator.
2.6392.
What is the gain of the lag compensator?
KC, which is 2.6392, Doctor. Oh,
That is lead compensator. What is the gain value of the lag compensator?
oh, 1.6246.
Where? Can you show the transfer function?
This one, Doctor.
Oh, lead. There is no lag, only lead. Okay.
Yes, we only design that. No,
Why you don't use lag compensator? Why you use lead compensator?
because the steady state error is already 0. So we doesn't need to
Oh.
improve the steady state error using lag.
The statistic error
Yes,
is
Doctor.
zero due to
Due to the KV is already big. And 1 over KV, we will get it is 0.005 from task 1.
because the system is type 1.
System is type 1.
Type 1. Okay, proceed.
And this is the block diagram. I forgot to present. And from all the calculation, we get the GC of the lag compensator. And this is the boot plot before applying the GC, which is from task 1. And after we apply the GC into the block diagram, we get that the phase margin, which is 40.4 degree, which is near to what our design, which is 39.1.
Okay.
And the radian per second is 99.1. And the peak gain of the closed loop both load is 3.36. So after applying the lag compensator,
Pas sikit, Din.
we
Maju sikit.
we get the magnitude, the peak gain is 1.4723, and the peak frequency is 81.3 radian second.
Payah baca,
And the
tak payah baca nombor tu. Just
okay,
indicate dia higher ke, lower ke, increase ke, decrease ke. Tak payah baca tu. Itu awak nak jadi pembaca berita ke?
is decrease. The peak
Dah,
gain
tu
decrease,
je. Stop.
and the omega bandwidth increase.
Hmm.
Next, this is the Simulink. The blue one is after compensated, and the black one is before. And by using step info in the MATLAB, we will get that the settling time of the new outcome is 0.0771, and the overshoot percentage is reduced to half. And this is using MATLAB. And this is the MATLAB coding for the all. That's all the
Okay.
okay.
So
Pastor.
I will continue with the task 6 is the result analysis and discussion. So from this table, by comparing the first design is the best design and the second design with the PID controller and the last design is with the lead compensator. Based on these three design, with the lead compensator have the best performance, which the rise time is the shortest and the settling time also shortest, and the percentage of overshoot also approximately match the desire, which is 30%, and the peak time also shortest, and the stability also remains stable. So for the task 3, the rise time and settling time, um, the rise time and the peak time will become longer a little bit because by changing the control parameters, the KP and the KD will somehow affect the transient response. So by using the PID tuner, we will get the optimal best performance and the best parameter to achieve this best performance of system. Yeah, that's all for our group. And the conclusion of
So in conclusion, all the objectives were achieved. And so we can see that the system can be analyzed in both time domain and frequency domain. So using the time domain analysis, we can design a PI, PD, or PID controller. Then using the frequency analysis, we can design a compensator, a lag lead or lead lag compensator. So we saw that from just now in task 6, we could conclude that the PID tuner gives us the best results with 0% overshoot and 0 steady state error. So these are our references. And thank you for your time.
Okay, thank you. Sharing. Thank you. Thank you.
Thank you.
You Wong, thank you.
So,
Good job.
so I start sharing.
Yeah, stop sharing.
Okay.
Okay, last group. Group number 6. On video. Group number 6. Last group. 8. Miss Lo Zixuan. 8-nya. Silakan.
Let's good afternoon, Doctor. We are from Group 6, and these are our team members. Next slide. And these are our team members. For information, we actually have 4 members, right? But one member is, you know, that he's a free rider, so we did not include him. So next.
He has
So,
a heart problem, sakit jantung.
So in this assignment,
Jantung tersumbat.
Oh, yeah.
Jangan marah dia, nanti dia sakit jantung.
Oh, okay.
Dia tak tahu ke?
Tak tahu.
Tak apalah. Let me handle it. Okay.
So in this assignment, we basically focus on the analysis of aircraft altitude control system by using root locus technique in both time and frequency domain, and also the implementation of modifying the system by using PID controller and also lead lag compensator. Next. And this is a system block diagram as well as the parameter values given. Next. So the objective of our assignment is to analyze and optimize the aircraft altitude control system, to study the performance of the aircraft altitude control system in both time and frequency domain, and also to improve the system by using the PID controller and also lead lag compensator.
Next. So in the task 1, the equation is successfully shown by using the block reduction method, and these are the steps of getting the equation.
Okay. Okay.
Going to task 1B, we need to get the open loop transfer function using the parameter given just now. So I just insert the value for each parameter and we'll get the GS here. And going to task 1C, we draw a block diagram using this unity feedback system, and our controller gain is 90, and the closed loop transfer function will be this TS. And going to task 1D, we need to perform the open loop and closed loop transfer function using the MATLAB coding. So this is the coding, and the results show in the MATLAB.
So in task 2, we basically focus on the time domain analysis. First, by using the root Hurwitz table, we're able to find the range of stability of the system. And the result we get is 0 until 246.09. Next, by using the critical gain, we are able to find the J omega crossing point, which is 1029.2. And then we use the differential to find the breakaway point, which is around negative 246. And this is the root locus that we sketch. So next, after we get a value, then we run a simulation by using the MATLAB. So from the plot, we can observe that the values are all accurate, which is negative 246 and negative 1030, which is accurate.
Going to task 2C, we need to do the time domain analysis. So we perform the open loop transfer function using the MATLAB coding, and also we use the step info function. So this is the step response graph we get, and also the output parameter here. So we can see here the settling time is 0.03 second and overshoot is 54% around.
So now we are going to analyze the system in frequency domain. Next. So this is the open loop transfer function block plot in MATLAB code. We just use the block function. Next. This is the block plot, and we can see that the gain margin is 8, phase margin is 22, and the stability is stable since the gain margin is positive. And the range of stability, we can just shift the gain margin to 0 dB, and we can get K equals to around 246, almost same as the time domain analysis. And then we can get the statistic error is 1 over KB, where KB we can get from block plot, which is 593. So we will get the ESF is 0.017, which is almost equals to 0. Next. This is the closed loop block plot function, MATLAB code. Next. So from the block plot, we can see that the magnitude is 9.63, and then the damping ratio can be found by using the equation by substitution. Then we can get the zeta is 0.16. Then by substitute the zeta into the percentage of overshoot, we can get that the overshoot is almost 58%. Next. Then to get the peak time, we also just substitute this equation by substituting the omega p and zeta that we get just now, and we will get 600. Then by substituting this omega n and the zeta, we will get tp equals to 0.04. And the settling time also by substituting, we can get 0.03. Next. So by comparisons of the time domain and frequency domain, we can see that all the parameters are almost similar, so that our calculation is quite accurate.
In task 3, we design a PID controller to modify the system performance. Next, first we need to identify the system, the design specification. So the design specification that we want to achieve is to reduce the original percentage OS and the setting time by half, which is 53.5% to 25% and 0.03 seconds to 0.015 seconds respectively. So this is a closed loop block diagram for the system with PID controller. Next. So with the percentage OS we targeted, which is 25%, we are able to find the zeta value by using the zeta value formula. So the zeta value we obtain is 0.404. And with that, we are able to obtain the value of the omega n by using the settling time formula. And after that, we are able to find the new dominant pole. With the new dominant pole, we are able to find the location of the Z, the zeros location for the PD controller by using the angle property. Next. So after using the angle property, we get the new zero value, negative 1631.79. So after that, by using the gain formula, we substitute the value of dominant pole inside the gain formula, then we can obtain the new gain, which is 0.0505, which is also equal to the KD value. And after that, we can find the KP value by using the KP over KD equals to the zero value. And the result we get is 82.405. So since the steady state error of the original system is almost zero, so therefore PI controller is not used. So the KI is equals to zero. So this is the compensated system formula. Next. After that, then we use a MATLAB to simulate the PID controller system, the system with PID controller. So from the graph, we can see that the percentage overshoot is around 26.2, which is close to our targeted value, and the settling time is 0.0126, which is also accurate. Next. Then we run the simulation again by using Simulink. So this is a block diagram in Simulink. So from the graph, we can observe that the value is accurate, which is similar to exactly to the MATLAB code. Next. Yeah, from that, we can observe that the settling time is 0.0124. For information, it's 0.5124 here because we set the time step to 0.5. So the settling time should be 0.0124. That's it. Next. So yeah, from all the result we get, it can be set which is accurate and similar. Yeah, with the design met our expectation.
Going to task 4, we are using the BID tuning controller. So it's very easy. We just using the Simulink file from task 3 and using the tune function inside the MATLAB. So this is the output response in tuning of BID, the graph. And after showing the parameters, this is our output for tuning. Then this is the comparative analysis. So you can see here all the gains. For example, the KP, KI, and KD is tuned to the minimal set point, so can achieve the desired performance. Then the system is actually enhanced by showing a lower rise time, peak value, and percentage overshoot. But here the setting time actually after tune is a bit higher, is because for block PID, it has higher overshoot. So actually the setting time is smaller.
So now we are going to task 5. Next. So we are according to the design specification on task 3, which is OS and TS reduced into half. Next. So this is the closed loop block diagram that includes leak lag compensator, but now because our KI is equals to 0, we just use the leak compensator only. Next. So since the ESS is very small, leak compensator is used instead of lag compensator, and the design specification here is get from the previous task, and the most importantly is the ESS, which is 0.017, and we can get the KV equals to 588. Then by using the 588, we are able to obtain the K value, which is the pre-amplifiers that satisfy the ESS. We will get K equals to 50.35. Then we will get the new transfer function, which is like this. Next. Then we will need to find the phase margins of the uncompensated system when the OS is 25. So from the graph, we can see that the zeta is equals to 0.4 and the phase margin is 43.5. This is the MATLAB code of the GNU function. Next. And this is the dot plot. Then from the dot plot, we can see that the gain margin is 13.8 and the phase margin is 36.4. And the max phase margin is the previously get 43.5 minus this 36.4 and plus a 10 degree of a correction factor, and we will get 17.1 degree. Then we will get, we are managed to find the beta needed, which is 0.5. Then we will manage to find the compensator magnitudes by using this beta, and we will get 2.6. And in the previous slide, we can see that when it is 2.6, our gain, our omega max is 564. So next slide. By using the omega max, we can obtain the ZC and PC. Then we will manage to get the compensator transfer function. Then this is the final compensator open loop transfer functions by multiplying the GNU and the GC. Then this is what our lead compensated open loop transfer function. Then this is the MATLAB code. Next. This is the open loop transfer function spot plot. Next. This is the closed loop transfer function MATLAB code. Next. And this is the dot plot of the closed loop transfer function. Next. So from the step info, we can see that our settling time is 0.013, which met our specification 0.015, and the overshoot is 22%, which also met our specifications 25%. Next. So by using the same methods that we use in the frequency domain, we also can obtain that the overshoot is 22.4%. Next. This is the Simulink, and from the graph, we can see that the TP, TS, and OS all met our specifications. Next. And this is the comparison between the task 3 and task 5. We can see that all specification is met since the both OS and TS met our desired value. And this is the extra one where I see that Doctor, you got put in the slide, so we just compare. So between the comparison between the uncompensated and compensated system is that in the compensated system, we can have a higher gain margin so that we have a higher range of K. Next. Then this is the closed loop transfer function comparisons, where we can see that the compensated system has less overshoot and smaller peak. Next.
Going to task 6, so this is the parameters we get from the task 2. So we can see here that actually the percentage overshoot is quite high, and also the setting time we can improve. So our design specification is basically based on these two parameters. So from the parameters from task 3, which are using PID controller, we can see here we added 10 at negative 1600 here to improve the system response. So we get the gain value for PID controller, and then we managed to improve the system to the design specification, which is percentage overshoot around 25%, and also setting time around 0.013 seconds. Then for task 5, using the lead compensator, we also managed to meet the specification. As you can see here, we calculate the target phase, the required phase margin, which is 17.1 degree, and we get setting time is almost 0.013 seconds, and percentage overshoot is 23%. So what are our finding is both PID controller and lead compensator actually met the specification, but we can see that for PID controller, it's balanced in all improvement in both percentage overshoot and setting time. But for lead compensator, it actually just excelling in fine-tuning specific performance characteristics for our group, is especially in reducing the overshoot. So we can say that PID controller is actually more widely applicable because it have a balanced function for all the parameters we need to improve. But for lead compensator, it's actually more suitable when you want to improve a specific parameters, and you need to fine-tune it, and such as the reducing of overshoot here. So our conclusion is our objective to enhance this system performance using PID and lead compensator has success, which reduce the overshoot and also faster setting time, and the steady state error is equal to 0.
Right.
So this is our reference. That's all from our group. Thank you.
Okay, looking good. I don't see any error. Very precise, tidy. Okay, so thank you very much. You may go exit now. Okay.
Thank you, Doctor.
Thank you, Doctor.